Hi, I am Prashant Kumar, Assistant Professor, Department of Computer Science and Engineering, MS Engineering College, Bangalore. In this video, I am going to explain machine-dependent assembler features. In the previous video, we have seen assembler data structure and algorithms, how the pass 1 and pass 2 will perform with respect to the machine SIC, Simple Instructional Computers. Now we are going to dig a little more about assembler and its features. So its features is classified into two categories. One is machine dependent features and second one is machine independent. First we will see what is machine dependent features of assembler and why we call it as a machine dependent features of assembler. In these features is purely depends on the underlying architecture. We will write the code based on particular architecture. Suppose that architecture support a set of instruction format, a set of addressing mode, then we will consider those features while writing the assembler code and writing object program. So such features are categorized under machine dependent features. We will see what are the machine dependent assembler features. There are two machine dependent assembler features we will consider here by considering the architecture SIC, XC and SIC. Two machines we have, one is Simple Instructional Computers and second one is Simple Instructional Computers Extra Equipment. These are the two categories, and the second one is a extended version of the first one and it is upward compatible. So the object code that we run in SIC we can also run in SIC, and these features will explain with respect to SIC, XC and SIC. Let us see in SIC, XC we know that it supports different set of instruction formats and addressing modes. Few addressing modes I have categorized here. First one is PC relative or base relative addressing. So we can write like this. So relative addressing coming under relative addressing mode. The next one is indirect addressing mode. So we can write instruction in this way where we will put at the rate just beginning of the operand. Then immediate addressing mode where we will write a hash symbol to understand it's an immediate addressing mode. And if it is an extended format like writing some instruction belongs to format 4, then we need to put plus at the beginning of the instruction. In indexed addressing modes, definitely we will get an index register as an operand. So we will write this way where OP indicate operation code. In SICX also supports some register to register transferring instructions. So that also categorized here. SICXC support this type of addressing mode in instruction format. So we can utilize those features while writing the assembler code and converting this assembler code into object code of SICXC. That's why this feature is coming under machine dependent feature. This is the same program that our data transfer from the input device to output device that we have seen and we have studied for SICXC, and that program is rewritten and which is suitable to SICXC machine. Here we have considered SICXC features, machine dependent features exclusively we will discuss here, and the program is rewritten and which will help us to improve the programming as well as the object code created by the assembler. The first thing is you can see this here. Usually in SICXC start followed by we will write operand, and operand is a memory address, but in SICXC it is 0, and which we have written purposefully for writing object code as a relocatable object code. So we know that what is a start. Start is assembly directives which will help us to understand the beginning of the program. And this instruction STL return address is a relative addressing mode instruction, and here you can see that load data length into B register is immediate addressing mode instruction. That's why hash symbol at the beginning. Then here you can see that plus symbol, so that is a instruction coming under extended format 4. See another immediate instruction, a comparison instruction, we are comparing with the 0, immediate value 0. Yeah, so here this Ampersand indicates an instruction belongs to indirect addressing mode. Jump at the rate return address. Then see here, this is the subroutine for reading the record from the input device and will store it into a buffer. Read the record a byte of data and it will store it into record. So one instruction you can see, but it's a return in register to register data transfers. Compare register to register where A and S are the two registers. This is the another subroutine, and where this is help us to write the data which is present in the buffer onto an output device. So this program is the main program which will call the subroutine read record. You can see here read record is here for reading the data from input device, and after that it will call the write record for writing the data from the buffer onto the output device. Let us see few statements in the above program where we have used SICXC features, instruction format and addressing mode features. We have rewritten few instructions and how those instructions will help assembling as well as object code generation. On fifth line, one instruction is there, copy start 0. Start 0 is an instruction to the assembler that where the program will start at this log. Since we are using object code is a relocatable object code, that's why we kept operand as 0 and the program name is copy. And more about relocatable program we will discuss later. And second one is very important, in SICXC support register to register transfer instruction. Such cases, look at here, one instruction compare R A comma S, where A and S are registers. We are comparing the content of A and S, and the object code you can see that is very simple, and creating object code is very simple because there is no need for any memory reference. Directly we can convert this type of register instruction into object code because it compare R, it's a mnemonic code, operation code, its object code is A0, and A accumulator object code is 0, S register object code is 4. So that is the way we have listed the registers. There are many registers SICXC support. All these registers are this one, and its value is shown here. And how we can get the register value? There are two methods. One is we can use a separate table, and in that table filled with the registers and its value. Otherwise we can use a simple table where we are using SIC assembler, and that data structure as it is we can use it, but that symbol table is preloaded with this register value and register name. These are the two options. The advantage of using register to register instruction is, here there is no memory reference, and execution of register to register transfer instruction is fast compared to any instruction which referring memory, because registers are more cross. Also the object code creation is fast. So next type of instructions are register to memory data transfer instructions. There are two categories. One is program counter relative and base relative addressing mode. The instruction belongs to program counter, where program counter content we will use, and instruction belongs to base relative, where base register content we will use. In format 3, suppose the instruction is in format 3, the displacement is 12-bit, that 12-bit address field. So the maximum displacement that we can store in the 12-bit field is 4096. So the displacement is from 0 to 4095. Then if it is using PC relative, then the displacement we can store from minus 2048 to 2047. Here also 12-bit maximum, but the thing is the reference with respect to PC we can do in two ways. One is forward reference. Forward reference you are using, then maximum you can refer up to the instruction belongs to 2047. If backward reference we are using, then we can refer the instruction up to 2048 in the backward direction, previous memory locations. If you want to refer any a memory location which is beyond these 4096 locations, then we need to change the instruction format into format 4 instructions. Format 4, the maximum displacement we can use in SICXC is 20-bit. So 20-bit means we can address up to 2 raised to 20. So SICXC maximum memory is 2 raised to 20 bytes. So the entire memory we can address by using 20 bits. Since SICXC providing extended format instruction, that's why in assembler we can write the instruction by utilizing those features. Then there are certain addressing modes are also support SICXC, immediate addressing mode, indirect addressing mode, symbol addressing mode, etc. One example we will see how to generate object code and displacement if it is a memory reference instruction where program counter is the main reference, where program counter relative addressing mode we are checking how to calculate displacement. Yeah, if it is program counter, we know that the displacement is from minus 2048 to 2047, so maximum of 12 bit. So program counter will point to the instruction to be fetched. Then after fetching that particular instruction, the program counter will automatically increment and point to the next instruction. So let us see, suppose an instruction, initially a program pointer point to this location, so that location contain the instruction first STL return address, store return address into L register. That is the meaning. After fetching this instruction, program counter point to the next instruction, where we can see that next memory location is this one because it's a 3-byte instruction which point to PC point to 0003. And return address is a label, a mnemonic label, and that label address is 0030. Then the target address is PC plus displacement. So that is the target address. Then displacement is equal to target address minus PC, which is equal to 0030 minus 0003. So the displacement is 02D. So opcode is 000101. This is the opcode bits, and there are few flag register NIXBPE. Since it is a format 3 instruction, that's why E is equal to 0, and it's a program counter relative instruction, that's why P is equal to 1. Then N and I is equal to 1. Then displacement is we already calculated 02D. So the object code generated is 17202D. 1, this is 7, this is 2, and 02D. So this is the final object code. Okay. Next case is base relative addressing mode, and in this category the displacement is again, if it is a format 3 instruction, the displacement is 12 bit. So it's starting from 0 to 4095. Up to that much displacement we can incorporate in the instruction, but base register is under the control of the programmer. The programmer must tell the assembler what the base register will contain during the execution of the program. Yeah. So there are two assembly directives. One is base and second one is no base. So these two assembly directives will help us to use base register and to define instruction in base relative addressing mode. See, this base is a assembly directive tell the assembler what the base register will contain, and no base tell the assembler that the content of the base register can no longer be used for addressing. For example, here you can see that load B register the value of length, then base length, that means base register contain content of length into base register, and after that you include base relative instruction belongs to base relative addressing mode, and if that base register is no longer required, then you can use no base assembly directive. Then how the assembler will perform this relative instruction and target address calculation of the instruction which belongs to relative addressing mode. See, by default the assembler will take the instruction which is program counter relative. If the instruction in format 3 is in the format of thing related to memory, then it will by default it will take PC relative. The assembler first choose PC relative. If the displacement is not enough, suppose our displacement is beyond our limit of PC relative displacement, then it will take base relative. For example, if the range is beyond minus 2048 to 2047 plus 2047, then it will consider it as a base relative. Summary: the programmer must specify the extended format for byte by using the prefix. Suppose we want the displacement more, then specify the programmer should specify the instruction explicitly. It is a format for instruction. Then maximum get a displacement of 20 bits. If not, that means programmer is explicitly not mentioned in the instruction, then the assembler by default will take it as a PC relative. If the required displacement is out of range, it will use base relative addressing. Still the required displacement is beyond the range, then the assembler will generate an error message. This is the situation. Another example for another class of instruction, immediate addressing mode. Here there is no means of memory reference. So if the immediate mode is specified, the target address becomes the operand itself. So here you can see load, see if the line 0020 is the instruction where the instruction is load accumulator #3. So this is the operand, it's a immediate value, and then load 03 into accumulator, that is the meaning of the instruction. The target address is in 0003, and you can see the instruction format, instruction in for object code op 00000. This is the operation code of LDA. Then I become 1 because it's an immediate addressing mode. X, B, P all are 0. E is also 0 because it is not an extended instruction, and displacement 003. So final you will get an object code of 01 in hexa 010003. So another example where immediate instruction but it is in extended instruction format. So another different categories of instructions. We are discussing more about these instructions. These are examples. So one subtopic is over where we have discussed instruction format and addressing mode. And why it is dependent means these features, instruction format or addressing mode, both are machine dependent. We are considering those features while writing the assembler and object code, then it is a machine dependent. And the next machine dependent features of the assembler is program relocation. And why we need program relocation? So it is desirable to load and run several programs at the same time, because if we have enough memory to load multiple programs, and those free slots if you are using for loading multiple programs, then we need to use program relocation. The system must be able to load program into memory wherever there is a room. So in such a way we need to write the object code. The exact starting address of the program is not known until load time. So what the assembler will do is assembler will create object code, and the loader will load the object code into the memory wherever the room is available. For example, here we can see that we have a assembled program, and object code is loaded into the memory location starting with the 0000, and here we have a extended instruction format, a jump subroutine read record, and its object code is this one, and the program will end at here 1076. While running one time, we can load the program into this memory location. Okay, next time suppose you are running the same program, it may load it into another memory location starting with 5000, and if the program is loaded into 5000, then our extended one example for the extended instructions, and which referring a mnemonic label read record, and third time suppose we are running the same program, it may load it into another memory. It may not be the same memory location, it may be different memory location. Here you can see the another example. We have loaded into 7420, and our instruction, its object code is this one. So ultimately you can see if the object code is a relocatable object code, then we can load it into any of the memory location wherever we have the enough space to run that object code. That is the concept of relocatable object code. Previously we have studied object code, that is an absolute program, absolute object code, and those absolute object code we can't load in different memory location. Program with starting address specified at assembly time. In absolute program, assembler will specify where is the starting address of this object code, and we have to load the object code into that address, that location only. The address may be invalid. Suppose the program is loaded into somewhere else. Suppose we are loading those program into object code into somewhere else in the memory, then the address is invalid, then the code we can't run. So simultaneously running multiple program, we want what? A relocatable object code. So the relocation is a property which will help you to utilize our resources effectively and efficiently. The only part of the program that require modification at load times are those that specify direct address. So by creating relocatable object code, we have to take care of some instruction in the assembly language and its conversion into object code. Where we need to focus more on is, suppose any instruction which for a mnemonic label, and the rest of the instructions need not be modified. Why? Because for example, if it is an immediate addressing mode instruction, an instruction which is immediate addressing mode, there is no memory reference, there is no need to modify while creating relocatable object code. And if it is if the instruction is a PC relative or base relative, then also there is no need to modify those object code. Why? Because the content of PC is decided when the object code is loaded into the memory. So PC value will change wherever reloading. So PC relative instruction will not create any problem. Similarly, base relative, the base register value is also a programmer is loading the content, so that also will not create a problem, because if the instruction is referring a direct memory address, then once we creating the object code, it is difficult to identify which is the actual address and which is the constant. The assembler must keep some information to tell the loader. So assembler will create relocatable object code, then the loader will load that relocatable object code into memory wherever the memory is free. While creating relocatable object code, the assembler must keep some information to tell the loader that these all are the instruction need to change. The assembler will keep few information, and that information is a instruction to the loader regarding the modification of few instruction while loading the object code into the memory. So what is that few instruction and all, we can check. The way to solve the relocation problem: for an address label, its address is assigned related to the start of the program. So if you are creating a relocatable object code, then the operand of the start instruction is 0. This will create the relocation become easy, and produce a modification record to store the starting location and the length of the address field to be modified. For every instruction which is referring the memory address directly, assembler will create a modification record. That modification record, it is one of the records as similar to the text record. What we will store in the modification record is the starting location and the length of the address field to be modified. The command for the loader must also be a part of the object program. Now look at here, this is the format of modification record. So column 1, first column contain M to indicate the modification record, and column 2 to 7 contain the starting location of the address field to be modified relative to the beginning of the program in hexa. Column 8 to 9 contain the length of the address field to be modified in half byte. One modification record for each address to be modified. Suppose 3 addresses are there in the program which we need to modify while loading or creating the relocatable object code. There are 3 direct memory access, then 3 separate modification code to be created. The length is stored in half byte, that means 4 bits. The starting location is the location of the byte containing the leftmost bits of the address field to be modified. If the field containing an odd number of half bytes, the starting location begins in the middle of the first byte. For example, you can see that here from 4B1 01036 is a direct memory reference where Here it is nothing but our jump instruction, jump subroutine, and with respect to this instruction there is a modification record, and in the modification record you can see that first field is EM, then remaining few fields are 000007, last field is length. This is the starting address and this is the length. So for B1 is the leftmost 3 hexadecimal digit, and remaining 101036 is what 20 bits in the rightmost side, and this is another case. This is another 3 address we need to modify. So with respect to these 3 addresses there are 3 modification record. So this object code is a relocatable object code. Thank you for watching the video. Thank you.